We're going to start looking at equations. The first step is to make sure that we can understand what any equation is telling us. So let's have a look at an equation like this one, 5x equals 15. What does it actually say? Well, first we need to focus on the 5x and remember that in algebra, when we have 5x, what we mean is 5 multiplied by x. So what is this equation saying? It's saying if we take a number and multiply it by 5, it'll be equal to 15. A number multiplied by 5 is equal to 15. And hopefully you can easily see that the answer here will be that that number must be equal to 3. So the written translation of that is a number multiplied by 5 is equal to 15. I want you to try this for yourself. I multiply a number by 3 and then add 1 and get the answer 7. What is the number? See if you can translate this into an equation. Pause the video now and try it. Okay, did you start like this and say, I'm going to take a number, any number, so I'm going to call that x. You could of course have used any letter you wanted to, y, a, b, z, anything. But let's start with x. I take that number and I multiply it by 3. That's just going to give me 3x. Then I add 1 to that, and it is equal to 7. And there is the equation that goes with that sentence. Can you think what the number might be? What number, when multiplied by 3, and then you add 1 to it, gives you the answer 7? Hopefully you can figure that out in your head, that the answer to there has to be 2, because 3 times 2 is 6, plus 1 gives you the 7. What does it mean if we say a number is a solution to an equation? Let's explore this by looking at the equation 5x equals 15. This equation says if we take a number and multiply it by 5, we get 15. If we ask ourselves the question, what number multiplied by 5 is 15? Hopefully we can easily see that that is 3. And so we say x is 3 is a solution to the equation. And we say that it is a solution to the equation because when we put x equal to 3 into the equation, it makes the equation true. If we put x equal to 3 in here, we get 5 times 3, which is equal to 15. So x equal to 3 is a solution to the equation. Let's look at something that isn't a solution. For example, x equal to 2 is not a solution to this equation. Why? Because if we put x equal to 2 in this equation, it won't be true. Let's see. Let's put x equal to 2. What we're going to get is 5 times 2, which is 10. And 10 is not equal to 15. What if you were asked, is x equal to 1 a solution to the equation x squared plus 3 equals x cubed minus 2? I'm not expecting you to be able to solve this equation at all. What we're wanting to ask is whether x equal to 1 is a solution of this equation. In other words, if we put x equal to 1 in place of x, will we get exactly the same here as we get here? Well, let's have a look. When x equals 1, the left-hand side of the equation is going to be 1 squared plus 3, which is 1 plus 3, which is 4. And when x equal to 1, the right-hand side of the equation is going to be 1 cubed minus 2, which is 1 minus 2, which is negative 1. So when we take the value x equal to 1, This side of the equation gives us the answer 4. This side gives us the answer -1. And 4 is not the same as -1. In other words, putting in x equal to 1 in the equation does not make the equation true, does not make the two sides of the equation equal to each other. And so our answer is no, x equal to 1 is not a solution to the equation. When you start with an equation, you've got two sides equal to each other. As you work with the equation, you want to make sure that you keep those two sides equal to each other. So the golden rule of equations is going to be that what you do to the one side of the equation, you have to do to the other side of the equation so that you keep it balanced, so you keep those two sides equal to each other. Let's have a look at this. Let's illustrate this using a sweet equation. Imagine that I have these two tables, and on these two tables I have exactly the same number of sweets. So here and here are the same number of sweets. The only difference is in this one the sweets are still in the box, some of the sweets are still in the box, whereas here I've unpacked them all. But the number of sweets on both these tables is exactly equal. I want to figure out now how many sweets are in this box here. And to do this, all I'm going to do is make sure that I align what I do on both the tables. So for example, if I take 2 sweets off this table, if I want to make sure that I've still got the same number of sweets on both the tables, I need to also take 2 sweets off this table. Still having the same number of sweets on both tables means that in this box here, there has to be 1, 2, 3, 4, 5, 6, 7 sweets. Let's do one more quick example. We have the same situation, 2 tables that have exactly the same number of sweets on them. But this time there are 3 boxes. We don't know how many sweets are in a box, but we do know that all 3 boxes have exactly the same number of sweets as each other. So let's try and work out how many sweets per box. Well, we can start by taking 3 sweets off this table, but we then also need to take 3 sweets off this table so that we make sure that the number of sweets on each table remains the same. We can then take a box off this table, but if we do that to keep things the same, we must take a box off this table. So we know we now still have a situation where there's the same on same number of sweets on both tables, and so we know that the number of sweets in this box is equal to 10. And this is what we will be doing when we solve equations. As long as whatever we do to one side of the equation, we do to the other side of the equation, we ensure that we keep things equal, and so we are able to solve the equation. We're going to have a look at inverse operations and how they are used in solving equations. To start, let's imagine we have this function machine which takes any input and adds 3 to it. So if the input is 5, obviously the output, when you add 3 to it, will be 8. Now the thing we want to be looking at today is, what if we know the output? How do we get back to the input? So if we know the output is 4, what we're asking ourselves is, what plus 3 will give me the answer of 4? And hopefully that's fairly obvious. The answer is 1. How do we get to that 1, the answer of 1? Well, one way we can think of it is that to get from 4 back to 1, we've subtracted 3. Subtracting 3 is the inverse operation of adding 3. It's the opposite operation. It undoes what adding does. So to get back from 4 to 1, we need to undo the adding of 3 by subtracting 3. Let's have a look at another example. Imagine now you've got a function machine that's multiplying by 4. Well, if you took your 5, you multiply it by 4, the output will be 20. Again, what we're more interested in now is figuring out, if we know the output, how do we get back to the input? So what we're asking ourselves here is what multiplied by 4 will give me 12. Now hopefully you immediately know the answer is 3. But you could also have thought of it by using the notion of inverse operations. You've multiplied by 4 to get the output, so how do you get back to the input? You undo multiplication by dividing. The inverse operation of multiplying by 4 is dividing by 4. Let's have a look at a slightly more complicated example. Imagine we start with a number, any number, and we're going to just call that x for now, and we divide that number by 3, and then we add 4 to that number, and we get the answer of 9. The question is, what was the number? Now you might be able to sort of think it out in your head. What divided by 3, and then after you add 4 to it, will give you 9 as the answer. But that's not actually that easy to work through in your head. And so what we're actually going to do is go slowly back through the inverse operations. So we know we ended up finally, after we've added 4, with the answer of 9. So what did we add 4 to get 9? Well, we can do the inverse operation, subtract 4, and see that it was 5 that we added 4 to get 9. Now we want to see what was it that when we divided it by 3 gave us 5 as an answer, and so we can do the inverse operation here and say 5 multiplied by 3, and we can see that we would have started with 15. Check that it's right. 15 divided by 3 does give me 5, plus 4 does give me 9. So simply starting at the 9 and doing the inverse operations one at a time gets me back to the number I start with. I know that it's 15 that when I input will give me the output of 9. Now let's see how this links to equations. So I'm going to go through the same example again, but this time put the equation alongside it. So we start with the number x, so there's the x in the equation. We divide that number by 3. Well, how does that look in an equation? Remember we've spoken about that division is just the same as a fraction line can be used to represent division, and so showing that your x is divided by 3, your number is divided by 3, can be shown like that. We then take what comes out of that and add 4 to it. So we must put that into the equation. And the answer we then get is 9. So we have to say that that is equal to 9. So this picture here represents the equation x over 3 plus 4 equals 9. Now to solve the equation we want to get back to x. Let's do exactly as we did previously. First, we're going to undo the plus 4, and that we undo by subtracting 4. Let's do that in our equation as well. And we see that we end up with 5. Now we need to undo the dividing by 3, and we know that the way to undo dividing by 3 is use the inverse operation, which is to multiply by 3. And what we've done here in the picture, we're also doing in the equation. And when we multiply by 3, we see we get to our answer of 15. We're now going to work with inverse operations to solve equations. If we have an equation like x plus 6 is equal to 10, what that means is we had an x, added 6 to it, and we got 10 as the answer. To get back to x, which is what we're trying to do when we solve an equation, work out what x is, so we just want to get back to x on its own, what we need to do is the inverse operation, which is subtract 6. Let's do that in our equation. Remember, with equations, what you do to one side of the equation, you have to do to the other. So let's subtract 6 from both sides of the equation. Here, plus 6 and minus 6 will disappear with each other, and you get x, and 10 minus 6 gives you 4. So the answer to this is 4. If we have a look at another one, like 5x is equal to 20. Again, let's think about what we're doing to x. x multiplied by 5 is giving us 20. Remember, when we write 5x, it just means 5 times x. We want to solve the equation. That means we want to get x on its own. We want to get back to the x, so we need to do the inverse operation, and the inverse of multiplying is dividing. In an equation, what we do to one side, we must do to the other. So let's divide both sides of the equation by 5, and 5 divided by 5 is going to be 1, so you just get back to the plain x you wanted. And then 20 divided by 5 is 4, and so we have our solution to the equation. A final example. Here we've got x over 3 is equal to 6. Now remember, if we write x over 3, that just means x divided by 3 is equal to 6. We want to get back to x on its own. When we're solving an equation, we want to get x on its own. How do we get back to x on its own? We do the inverse operation of division, which is multiplication. So we must multiply by 3. What we do to one side of the equation, we must do to the other. So let's multiply both sides of the equation by 3. That will mean you'll get back to x on its own on this side, and 6 multiplied by 3 will give you 18. So x is 18 is the solution to the equation. We're going to do another example of solving equations using inverse operations. And we do this example separately because it involves fractions, and we know how much everybody loves to deal with fractions. So let's remind ourselves about something about division of fractions. So let's just have a look. If I asked you to do 12 divided by 2 over 3, hopefully you remember how to do this, right? Division of fractions is a bit funny. What you do is you keep the first number the same, and then you change division to a multiplication, and you flip the fraction. So it's 12 multiplied by 3 over 2, and when you work that out, you get 18 as the answer. So another example, 8 divided by 4 over 5. Again, you keep the first number the same, you change division to a multiplication, and you flip the fraction, and so you get your answer here of 10. The important thing I want you to note is that dividing by 2 over 3 is the same as multiplying by 3 over 2. Dividing by 4 over 5 is the same as multiplying by 5 over 4. So dividing by a over b is the same as multiplying by b over a. Why is this important to me? Well, the kind of equation I want you to be able to solve now is one like this, where we've got 2 over 3x equals 6. What does that mean we have, right? If we've got 2 over 3x, well, when we don't put any sign in, it means multiply, right? 2/3 multiplied by x gives me 6 as the answer. So that's what my equation is meaning. So obviously, to undo the equation, I need to do the inverse of multiply, which is to divide by 2 over 3. But I want you to note what we've just discussed here. Dividing by 2 over 3 is just the same as multiplying by the flip of 2 over 3, so it's the same as multiplying by 3 over 2. So when we're faced with something, solving an equation like 2 over 3x is equal to 6, the way we get back to just a plain x is to multiply by 3 over 2. And when we multiply by 3 over 2, right, we're going to get back to x. Let's just confirm that. The 3's cancel with each other, the 2's cancel with each other, and so we get 1x, and of course we know 1x is just x. And then if we have to do 6 times 3 over 2, 6 cancels with a 2, leaving us with 3, and 3 times 3 is 9. So the answer to this equation is x is 9. Let's do one more example. If we've got 3/4 of x is equal to 15, and we want to solve for x, we now know that what we need to do to get x on its own is multiply by 4 over 3. And that will give us 1x, which is just x on the left, And then 15 multiplied by 4 over 3. Well, again, we can cancel the 3 with a 15 and get 5. And then 5 times 4 gives us 20.